Okay, we're going to look at complements of numbers. Okay. And the basic idea is that number complements are used to simplify the logic required for subtraction operations. So with a CPU, it's much simpler to do addition than it is subtraction. Okay. And the basic idea is if we set up the numbers or we make appropriate conversions of the numbers, we can actually do that. So we can do subtraction through addition. And we'll look at base twos, base we'll look at base 2 number systems and base 10 number systems. So the first part of this, what we'll do is look at coming up with the diminished radix and the radix complements. Okay, and then after that, we'll actually perform the arithmetic operations of the addition or the subtraction for that. So the general form of the equation for the radix complement, and the next one is the diminished radix complement, and then the radix complement. We'll look at both of those. Okay, so the idea is first you have. Okay, so here are the two formulas: diminished radix complement and the radix complement. So the r in this case is the base of the number. The n, lowercase n, is the number of digits. And the uppercase n is the actual number that you're looking to find the complement of, either the radix or diminished radix complement. So, for example, in the first case, let's say we want to find the nines complement of uh, this number here. Let's see, 546,700. Okay. So the 999,999 is basically, this is 10 to the 6, which is 1 million. We subtract 1, and then you come up with this number. Okay. Then you subtract out the n, or the number that your original number, and that gives you this number. So this is actually the nines complement of this number. Okay. And the next one is, here's the number for that, and they just you could go out one more digit. In this case, we go out one more digit so that the two numbers here have the same. If we want to do a math operation with these two numbers, the two numbers have the same number of digits. Okay, so that we perform that operation. So same thing here. Here's the number subtracting out from this, and here are your two numbers. Here are the two nines complement numbers of this is one of our original numbers, and here's another number that we're looking at. Okay. Now you can perform the same operation with ones complement. So this is if this was a to find the ones complement. If this is a base 2 number, we have 7 digits here, and of course we just duplicate that 7 digits here. This is 2 to the 7 minus 1, and then minus that value. Okay, and that gives you the end result if it's a base 2. You can perform the subtraction operation here. Okay, and same thing for this number. You'd come up with that result. And there's some more examples in the textbook, and actually gets in a bit more detail. But that's just the general idea, right? All you're trying to do is come up with the diminished radix complement of a number. And this is what it's giving you for this number, this number, this number, and this number. Okay? Then we have the radix complement. And the radix complement is just essentially the diminished radix complement adding 1. Okay, so you'll see that with the radix complement, it's essentially the same equation, except we're just adding 1. And just for comparison's sake, we can take a look at, here's the nines complement of, here's the nines complement of this number. And the difference between this number is just, its nines complement, tens complement is essentially just 1. Okay. And for the comparison between ones and twos ones complement, the next is twos complement. And you can look at the same result for that to see it. So you can go and perform the same operation here. Right? Okay, so when we perform subtraction with complements, essentially there's a couple of results. We could have a couple of two different types of results. One is that um, the operation is going to produce a positive number, and the other is, of course, it's going to produce a negative number. And how we actually handle that is slightly different. Okay, so the first thing is that if the minuend is greater than or equal to the subtrahend, well, the first number essentially is greater than the number that's going to be subtracted from it. Uh, any end carry, meaning that going into um, the next digit. So if anything carries over to the next digit, we essentially discard that, and we have the result is just the m minus n. Okay, so we'll take a look at some examples. The second one is that if it results in a negative number, okay, and it doesn't produce an end carry, and in this case, it it doesn't produce an end carry, and it's equal to just the radix, the number of digits minus um, the subtrahend minus the minuend. Okay, which essentially is just the complement of this, the r's complement of these the n minus m. Okay, and you know since it's going to be in terms of a complement stored in memory, it may not be apparent what that actually number represents. Okay, so we can look at that. So if we, the basic idea is if you wanted to see it in a form that you're familiar with, if you just do the complement of that sum and then place a negative sign in front of it, um, you'll be able to see something that you would be familiar with typically. Okay, so we'll look at a couple of examples here. So the first one, where the minuend is either greater than or equal to the subtrahend. Okay, so here's the minuend, here's the subtrahend. So here are the two numbers. First thing we do is we get the complement, which is done previously on the previous page, or at least following the process that was done on the previous page. So here's the number you would come up with for the tens complement of 3250. Okay, you add them together. Here's the sum, and then um, you just basically discard the end carry. And the way they do that is just subtracting out that end carry. Okay. And then the end result is just 69282. Okay. So you read that directly. So if this operation was performed with a computer, and what would happen is that the actual number that would be stored in memory would be the binary version of this. Okay. All right, now we have that's the second case. That's the second one here, or the first case here. Here's the second case, or the second potential result, is where the subtrahend is larger than the minuend, okay? Or more negative if you want to think about it that way. Okay, so the first thing is here's our minuend, and you come up with the tens complement of the subtrahend. And here's the result. So you have the result is 30718. Okay. And like I said, if it was, in a computer itself, this is like our general form. In a computer itself, it would be stored as a base 2. All right. Now, recognizing that when you're doing base 10, it's really kind of just showing you sort of the generic case first, right? And then we'll look at base 2. So in this case, all you have to do, get the tens complement of this sum, and then put a negative sign in front of it. So this is really what this shows you here is this is the number that what it's actually representing, right? In memory, this is the number that would be stored, or the two's complement of that would be stored in memory. Okay. Okay, so just continuing on. Now you can do the same thing with base 2. So here's like your x and y, and here's our minuend, subtrahend. Same thing here. Uh, and here's, you could do this. Yeah, well, x minus y. There's our first case, and here's our second case for that. Um, so here's the sum, and then you just subtract out this additional carry since there's six digits, right? So with the seventh one that goes over to the seventh position here, or the most significant bit here, that one is actually going to be the one that you would remove. Okay, so eliminate from it. Sorry, I should say the eighth position, right? Because um, there are seven digits. I don't know if I said six, but there's seven digits here. Okay, so the carry over to the eighth place gets subtracted out, right? So here's our end result. Now here's the second case in this one, and then you just do the addition. So here's my 2's complement of the x. Okay, and here's your final sum. So you're just doing addition, essentially adding these together, right? And then in the last case, so in here, all you do is you take it, get the 2's complement of this, put a negative sign in front of it, and this is like sort of conceptually what it would be being stored if you were working with base 2. Okay. And the other case, you could use 1's complement. I mean, it's just kind of showing you how you could be done. And in both cases, like in this case, you do an end around carry. So if you get carry over here, you bring it back around um, to the right and just add it in. And the second case, in this case, at the end, you just add 1 to it. So you do like, it's essentially like doing the 2's complement after the fact. Um, for the most part, we're going to be pretty much just looking at doing the 2's complement. Won't worry about this. Just another way to show you how you could do it. Okay. Okay, looking at signed binary numbers. All right. If a number has a so-called signed magnitude representation, we have to think about the most significant bit and what does that represent. Okay. Now, if it's signed magnitude representation, and if you've used if you've have done programming before, I hope you have, but when you're using a programming language, typically, and one of them is a good example is like C++, you can actually define a number as signed or unsigned integer value. And the basic idea is that if you have a signed number, that most significant bit is going to represent, one. If it's a 1, it's a negative number, and if it's a 0, it's a positive number. Okay. And we have a couple different ways of looking at this for the representation, and really it's talking about, is it a signed magnitude number system or a signed complement number system, right? In both cases, what you're going to find is that most significant bit is going to represent the sign. If it's a 1, it's it's a negative number. If it's a 0, it's a positive number. And comparing that with, if it wasn't a signed complement system or it wasn't signed magnitude system, that number, that most significant bit would just be part of the magnitude of that number. So one of the ways to think about this or to explain it is to look at some numbers and their relative 2's complement, 1's complement, and signed magnitude representations. Okay. So first thing is, if we look at a positive number, all right, like in this case, positive 7, and since we're not using that last bit, it really doesn't make any difference. But let's just take a look at that. So in all three cases, it's going to be the same. And all of these, of course, are all going to be the same until we get to where we have a negative number representation, right? If we have in each case, that essentially that last bit is used to represent the sign, right? Either it's positive or negative. Where the difference comes down is when we start to have negative numbers, and how do we handle negative numbers? This one is just 0, essentially. Okay. All right. And how would you come up with that? Well, they have positive 0 or negative 0 in this case. How would we come up with that? The basic idea is that, all you do is you come up with a 2's complement representation of this. You start off with, 0, 0, 0, 1. You flip all the bits, you add 1 to it, and here's your 2's complement representation. And of course, the 1's complement representation is just going to be 1 less than that. But what you'll notice that's consistent with all of these is that the leftmost bit is a 1, okay, for all of them, okay? But what you'll see when you go over to here, like I said, the 1's and 2's complement are only difference by adding, adding a 1 to this or subtracting a 1 to come over to here for the 1's complement. But the signed magnitude approach, you'll notice that essentially the first 3 digits are the same. Okay, the only difference comes out is the sign. So we're using this last bit to represent the sign. Okay, and that's really the difference between these 3 systems. And computers typically use this approach when handling numbers. Okay, continuing on. All right, so now what we want to do is take a look at some addition. Right, and the same thing. Now you can see the different possibilities we have here. We have where they're both positive, okay, which is not an issue, right? We're adding 2 numbers that are both positive. And the second case over here, essentially they're all additions, right? It's just a matter of which one of these are negative or positive. Here's our 4 different possible types of operations, right? Where the number, you add the 2 together, comes out a positive. Here's the other one where they're positive, but one of them's a negative number. In this case, the smaller number is negative. In this case, the larger number is negative. And in this case, they're both negative, okay? And we want to take a look at the result that we get. Well, the first case is really pretty basic and straightforward, all right? That's not an issue, okay? Okay, in the second case here, if we're going from left to right, we can see that in this case we have a representation of a number where we have -6. If we go back to the table, we'll see the 2's complement representation, -6, and we're using 8 bits. So of course the last 3 bits over here on the left would just be 1's, okay? And that's all this is. So you add the 2 directly. In this case, the end result is positive. So since it's positive, we just take the result directly as is, okay? And this is what we saw previously, when we talked about where the end result is less, or we can potentially call this the minuend and the subtend here. So if we go back and look in the case here, okay, we essentially have it where, the more positive number, the minuend is greater than or equal to n. So we just have the result is just where we have a carry at the end, and we just discard it, okay? The next case is the other case that we were looking at. And in this result, what you're going to see is there's no actual carry with this case, except what we're going to find is we'll have, if we were to have it, we don't have a carry bit to discard, but we have just the number itself. So we read it directly, okay? The only thing to recognize is that this is the 2's complement representation. So you'd have to do, find the complement of this and then add a 1 to it. I'm sorry, not add a 1, but put a sign in the end, and then you come up with a number, what it actually is. Okay. And the third case here is where we have both, and the same thing, when we'll have a carry in this case out to the left, and in this case, you just discard that. And as before, this is the 2's complement representation of the number, okay, that's stored. And as we previously did, if you wanted to go and here's an example with tens complement. But if you wanted to go and do that, what you would do is you'd come up with a two's complement of that number. Here it is. Two's complement of a number. Here's a good example. Two's complement a number and put a negative sign, and then you actually see the actual number that you would be more familiar with. Okay. But recognize that both this and this, the negative numbers, these are in two's complement notation. Okay. And then, so if they're stored that way in memory, if there's additional operations to be performed, the number's already in the right form for that to occur. Okay. So there's one more case we can look at here and think about is that, those were like additions, right? But we could also have a subtraction, right? And this gives you the basic idea of the process. Here it is in base 10, how you would do it. And if you think about it, it's really just minus 6 plus 13, right? Which is just what we had over here. And that's essentially what they're telling you here. It's like, if it was a subtraction, it's really just the addition of the inverse, right? So this one, just this negative and this negative makes an addition, and you can reverse these two, okay? And so what you would notice is that if you did, you'd come up with the same end result for that, okay? Performing this operation in, either in base 10, or in this case, base 2, okay? Okay, the next one's binary codes. And binary codes are basically just another way to, for you to represent the information that's stored in memory, okay? Now, with binary codes, the basic idea is you're taking a binary number and using it to represent the decimal symbol directly, okay? So there's cases where this is an advantage to do that. So what happens is that to be a valid binary coded decimal digit, essentially you only have this many. Anything more than this going up from, A, B, C, D, E, F, G, if you're talking about base 16, is invalid. So these are the only valid digits, okay, for that binary coded decimal digits. So basically you're taking 4 bits and you're using to represent your decimal number directly, okay? So, for example, this last case, we take the first 4 bits represents the 1, the next 4 bits represents the 8, and the last 4 bits represents the 5, okay? So that's a special type of encoding. All right, so now addition is going to be a little bit different. So if you had something encoded in BCD, you'll see that how we perform that operation. So to start with, let's say we have 4 plus 5. Now, 4 plus 5 in this case still results in a value of 9, which is less than 10. So because of that, this still results in a valid digit. Now, in the next example, we have 4 plus 8. So this would give us a result of 12. But of course, we can't just we can't represent if we're doing binary operation, what we're going to find is, of course, it should be 1 like this, right? We have 4 bits essentially for the lowest one and 1 bit for the lower digit, which would be the 2, and then 1 bit for the upper digit. So the actual mathematical operation to perform that, what you're going to do is add in 6, binary 6, all right? Or 0, 1, 1, 0. And when you do that, what it does is basically shifts the 1 over. So now it's part of the next group of 4 bits, okay? And here's another example. You're adding 8 and 9. You do the same thing. And so you end up with 17, and then when you add the 6 to it, you're going to end up with 1, 0, 1, 1, 1. All right. And the basic idea is you come up with a binary sum and you add 6 if it if it's, basically over 10. All right, sorry, over 9. So here's a kind of a quick example where you can actually um, perform these operations, well, with decimal numbers, and then make the conversion into a BCD after the fact. So the real kind of couple key points here is one, when you perform the operation, you first start off with, like, let's say here's the example, 375 minus 240. That's going to give you 135. And the way to do it here is, first part is come up with like the tens complement of this value, this 240, which is 9760. And the other value, of course, is just positive. So we just write it down directly. But the part that makes it a little bit different here is we have this, if you think about it, this is, if it was base 2, it would be 4 zeros. But this is um, 4 bits, BCD, right? Um, so we put the 0 over here because it's a positive number, all right? So we're basically pulling it out. So if you think about this is in binary form, you'd have 4 bits, 4 bits, 4 bits, and 4 bits to represent this, and this is um, the additional um, the additional value to represent the sign. Okay, so we go through, we add these two numbers together, and the end result is that from, when you carry these over, this is going to be 11, and you're going to have a 1 carried over here, which essentially just um, is the end of the 4 bits, right, for BCD, and you have a carryover into the next range of bits, which is just going to be the sign, and you just discard that. So um, this, you should be representing this with 4, 4, 4, 12, 16 bits. Okay, so these numbers would be represented with 16 bits. And this is just giving you kind of a quick example of the end result, right? If you add these two together, you get to come up with a 135 if you're doing it and you want to represent in BCD. All right. Okay. There's some other codes, and we'll just basically um, talk about these a little bit just so you're familiar with it. I don't think I'll be asking anything on these codes for the other codes. Just giving you kind of a quick idea conceptually that we have these different codes. Now, we looked at BCD, and if you look at the 2421 code, essentially this last place is just a weighting. So if it has the same weighting as this, and the end result is that um, you're coming up with essentially nine codes to represent that, to represent like from 0 to 9. What you notice with like 2421 code, um, when you go from the 4 to the 5, uh, it has a weighting of 2 here, so it's the same thing. So you're basically um, pushing out to be the next one. So when you're adding the next one, you're actually adding the weighting for this one. So there's a 2, here's a 2, and here's a 1. Okay. So just looking at these, like I said, the 2421. One of the things you'll notice is about the 2421 code is that it's essentially like the complement, and it's symmetrical about the digits. So from 0 to 9, you notice that 9 is essentially just a one's complement of that, or of 0. And then the same thing here. Here's just the complement of 1. The 7 is the complement of the 2, and the 6 is the complement of the 3. And then the 4 and the 5 are complements of each other. Okay. The XS3 code, this code is just essentially adding 3. So you're starting off with 3 to start with. Okay. And the last code has a different weighting system associated with it, the 84 minus 2 minus 1. And it's just kind of making you aware of these codes, that there are other encoding mechanisms out there for that. But you can see in this case, just starting off with everything 0. And then now, if you look at this, um, what you'll see is that this has a weighting of 4, this is a weighting minus 2, and here's a weighting minus 1, so that essentially just gives you a 1, right? And here, um, you'll notice the same thing. This is just 1 more than that. So it's a weighting of 4. This one has a weighting minus 2, so then the number is 2. Okay? So just basically recognize, that there are other encoding systems out there. Okay? There's another one, and this is the gray code. Okay? And same thing. I just want to make you aware of it. One of the things that gray code is used for is some kind of encoding where you have a rotating, like you're trying to encode maybe position of a motor, let's say a stepper motor or some other kind of motor, uh, and well, maybe not a stepper motor, but a motor that's rotating around. And one of the things that can potentially happen is that if you do the normal encoding sequence, you'll notice that there are places where you have more than one bit changing. Okay, so gray code takes care of that. The reason is that you might pick up like one bit changes, but the other one doesn't change when you actually are capturing that value. So gray code is just saying essentially that you're only changing uh, one bit at a time. And like I said, I'm not going to worry about um, going through the process or you needing to know the process of counting in that number. But what you'll notice here is that in this case, going from 000 to 1, the only bit that changes is the first one. Okay. And then the second one, the only bit that changes is this one. Okay. Now, one of the things that's you would notice that would be a problem is that if it went from 0001 to 0010, at that case, what would happen? You'd have two bits switching. So you could potentially, you know, not get the right code, read it improperly. All right. So that's basically the sequence of this. It's a 1 bit. You'll notice that with this encoding um, approach, only 1 bit changes each time. Okay? And they say, well, angular position of a shaft. Okay. Oh, there's another one, ASCII code. Now, when you're dealing with like Word documents, or, not text documents, I should say, in any kind of encoding scheme where you have information. What we recognize is that all the information is stored as binary characters, right? So it's like, how do you represent these special characters or letters and other symbols? Well, what they use is ASCII code, and the basic idea is that here's like the binary representation of that, and it's just in this case, um, uh, we have 4 bits representing these different symbols and different characters. So uh, what you would think about is like if they're all 4 zeros, this one just says that like the three the other 3 bits related to each one. So sorry, this is like the 7 bits to represent your code. So this one says, okay, here's B6, 7, B6, and B5. So there's B over to the left over here. Okay. So if it's 0000, all zeros, it's a null, which is just telling you it's a special character that's used. But let's look at something a little more interesting. Let's say if we had encoded the letter A, uppercase A, because uppercase and lowercase are different. So in binary, if you looked at the lowest, least significant 7 bits, what you would find is that it would be 1000001 would be stored in memory. Okay, so it's basically another encoding scheme, and what would be required is that um, the software has to know. It has to know that, oh yeah, I know that what's stored in that location is a ASCII representation of something. So when it reads that number back out that's stored in memory, it would represent it. If it was a word processor or a text editor or something like that, it would know that if that was stored in that location, like here, that would be the uppercase A. Okay. And there is, like I said, there's one thing to recognize here is that how it stores upper and lowercase letters is different. All right. But this is just another encoding scheme. Okay. Another way, you know, we have a computer, we have a system, digital system. It has information stored in ones and zeros. And it's like, how is that information interpreted? And it can be interpreted and stored in different ways or converted in different ways. Okay. And here's some other ones associated with that. Okay. There's some other things we do with, like there's error detecting codes, there's error correction codes, error detecting codes. Uh, the basic idea is that you're trying to transmit information. Let's say you're trying to transmit an A, and what happens is that there's a potential that you could get an error, right? It might be that one of the bits changes, and when it's communicated or it's received differently because of electrical noise or something else. So it's received an error, one of the bits. And how would you know that it has an error? Okay. So to give you an example, there's this so-called even and odd parity. So you count the number of bits that were ones, or count the number of ones, let's say. I have two ones. That's an even number of ones. So what you do is you take a zero and stick it on the end here. That shows you had an even number. Okay? And then if it's an odd number, you put a one on it. So I had three ones. So that's an odd number one. So then I put a one on it. So now when this gets received, if you're using even parity, okay, what would happen if for some reason this one of these bits got changed, you would receive three you would receive three ones, which should tell you this last bit should be a one, but you got a zero. So what you would recognize is that that's an error, right? An error occurred, right? And then of course with odd parity, it just reverses these two bits. That's all. Okay, it reverses the parity bit. Okay, so this is like, this represents the digit. This represents the number of, either there's an odd number of ones or an even number of ones. So when this gets transmitted, if there's an error in any of these, or any of them really, that you would get it would be the wrong parity with your end result. Okay, so this is what would be transmitted. You'd add that one other bit. Okay, binary storage and registers. All right. Now, in a digital computing system, digital system, essentially you're going to have each individual, what they would call cell, or down to the level of what we're concerned with, either is going to store a one or a zero. Okay. Um, Typically, we don't look at individual bits that are stored, although, you could, right? Typically, we have groupings of bits, and what we would consider this to be like a register essentially has that. Okay, and we'll look at that. Okay. And what it's telling you here essentially is that depending upon how it's used and what we had looked at previously is like what's actually stored. It's like how is that information interpreted, right? What is it, a code? Is it BCD code? Is it an ASCII character? Is it is it a two's complement system? Is it a negative number or a positive number? Okay. And then we'll look at the digital logic circuit. So this is the processing of information stored. Okay, so just to give you an example, this is, really kind of brief, but, information is stored as a bunch of ones and zeros. And if we look at, like, sort of conceptually, if we just take a look at this, we have memory, we have information that's stored in registers potentially, or memory units. In this case, we can think about it in terms of how we have information and how it's processed. Uh, you'd have like a pointer pointing to different places in memory, and you go through the operations of actually processing that information. So for like this is the keyboard. This would be like if you hit a key, and this one is if like some mathematical operation is being performed. Okay. So like if you hit a key, what's going to happen is you have a control unit essentially that's reading the information, converting that key stroke into, like, let's say it's ASCII equivalent, and putting that as 8 cells or eight bits essentially, and then going through the register, processing that information, and then store it in a memory register. Okay, so just a kind of a brief example of how this is done, right? A memory register is essentially like a unit of memory, if you want to think about it. Okay, so this is it's going and putting it into memory. So you have some process, convert, um, make the conversion from, like in this case, some letter is pressed, convert to that 8-bit or 8 cells if you want to think about it. In general, 8 cells, 8 bits. You go through process register and then it's stored in memory. Okay, or process unit, and then it's stored in memory. In this case, you have some memory units. Information is stored in two places. Let's say we're doing some addition or some operation with two numbers. So you have a number in one memory location, another number in memory location, goes to the CPU, does some processing. In this case, an addition, um, stored in a register. These are small registers on the processor, little memory units on the processor. An end result is generated, and then that's stored back into memory. Okay. Okay. All right. Yeah, stored back into whatever was zeros. I don't know why this end result didn't show it that way, but that's just how it is. Okay. The last part here is binary logic. Okay, so one of the things we're going to be we'll be looking at this extensively, is that there are three basic binary logic gates or logic operations. Okay, and the other logic operations that we're going to look at um, are based on these. Okay, so here's like if you did an AND operation, so you have two things. If you AND them together, you result in some end result. Here's like our Boolean. Here's our algebraic equation, Boolean algebraic equation. Okay, and if we think about it, essentially an AND operation is just multiplication. An OR operation is like an addition. And then the last one, I'm sorry, then not operation. So the basic idea is this: it's like if you do one or one, it's 1 0. If you binary arithmetic, and then in binary logic, it's 1 or 1, or 1 plus 1 is going to give you 1. Okay. Now, truth table is just something that's a table essentially that shows you all of the possibilities of the combinations, possible combinations. And here's like truth table for each one. What this one says, you need two things that occur, both to be true, in order for the output to be true. Otherwise, it's a 0, and that's an AND operation. A not's pretty easy because it's just the inversion. So if you had let's say this is a false, you get a true on the input. If you had a false in the input, you get a true in the input. If you get a true in the input, you get a false in the input. And what this one essentially just says, if one or the other is a 1, your output's going to be 1. So one or the other is true, the end result is true. Okay. Logic gates, logic levels, we'll take a little look at this some more. And this is where we're actually taking a look at a voltage on like the oscilloscope or our voltage meter. And what it says essentially is that um, how do we represent a 1 and how do we represent a 0? Okay. And if the voltage is above a certain amount, and this is our typical range for that, we essentially are going to call this a 1. If it's below a certain amount, it's a 0. So we have this sort of range where we don't want to be looking at it. What we want it to do is transition really quickly between these two. Okay, and we'll look at that some more. Here are the physical logic gates themselves. Like here's an AND gate, here's an OR gate, here's a NOT gate. And we can have more than just 2 inputs on these. We could have 3 inputs. Here's a 4 input gate. We could also have that too. All right. Now, we can look at it as a truth table, or we can look at, the time diagram where we can see things as they're happening, as they change with time. And this would be like what we would get on the oscilloscope, right? We'd be looking at ones and zeros. Okay. So if it was like in this case, this is these could be our inputs for our gates. And what you'll notice is that in this direction is time. This direction is like voltage or logic level, if we just look at it as 2 different levels. And what you'll notice that only when they're both 1s, if you got an AND gate, they become a 1. Okay. And in this case, it's one or the other will give you a 1. And the last one is just inverted. Okay. We're going to look at more gates than just, these three. But what we'll find is that we can always break them down, any of the other gates, to just these three basic gates. All right. And that's pretty much it for chapter 1.